So today we start off a new unit on exponential functions, which is really exciting. This is one of my favorites. Essentially, Algebra 1 overall covers three big families of functions. We start off with linear functions, which we've covered for many weeks, if not months now in the fall. And you were already familiar with the family of functions that are linear functions. And then the second one is exponential functions. And in the spring, we'll also talk about quadratic functions. But very similarly to linear functions, in this unit, we're going to explore all the characteristics of a function family that we call exponentials and what characteristics tie those together. So what are the common characteristics of the graphs for exponential functions, of patterns in their table? What do the equations look like? So all the characteristics that kind of group these guys together as exponentials. And we're going to introduce that today. So the big thing here is to understand what we're talking about when we say an exponential function and how is that different from a linear. Well, an exponential function, that's the first thing we're going to fill in here. So an exponential function is a nonlinear function that has this form right here. So this is the big idea right here. In fact, maybe we'll just write that nice and big over here. Okay, where a is not 0, because if we have a 0 here and we try to multiply that, of course, the whole thing is going to disappear. When we multiply by a 0, everything becomes 0. So a cannot be 0, b cannot be 1, and we'll talk about why that is in just a bit. And for exponential functions, b is going to be a positive number. So it's going to be a positive value, a positive base here that is not 1. Okay, now you can already see this looks very different than, for example, y equals mx plus b. And what really defines this or defines it as an exponential is the fact that our input, our value of input or independent variable, is in the exponent. So the input or the domain, those input values, is the exponent. Okay, and so we're going to explore what that looks like and what that causes the graph to do and the table of values and so forth. Okay, so you can already see, right? It's like, oh, this looks so different. That's why it's exciting. So an exponential function is always some number times a base raised to an exponent, and that exponent is what we're actually going to be tweaking and playing with in our input value. So these will be constants, and then it'll be raised to the x power. And so this might make you realize, oh, that's why we were talking about all that exponential property stuff, is because we're going to be dealing with things that have exponents. Okay, so let's take a look at what this graph looks like. So what I want to caution you on, I like this and I don't like it. So there's a couple reasons. There's really 4 different things graphed here. So each one of these curves is an exponential curve. They're just showing you what it looks like when a is positive, for example. Okay, so when a is positive, remember, a can be anything but 0. So if it's a positive number, then we're going to expect that particular curve to happen and live above the x-axis. Same thing here. This is when a is positive. So that means a positive a value. Okay, then that curve is going to be happening above the x-axis. If a is negative, so if this is negative, then, and then same thing here, a is negative, then the curve will be taking place below the x-axis. Okay, so this is not, exponentials aren't going to have 2 curves. It's either going to be this or that, depending if a is positive or negative. Okay, and so that's one of the characteristics. Notice it is a curve. It is no longer a straight line, and it is also a one-sided curve. And that's a really important concept that I'm going to focus on in just a moment. But it is a one-sided curve. And so you'll see it kind of come back up like some pictures you might have seen that are look more like a U shape. Those are the quadratics, and those are coming up in the spring. But these guys are really, you know, more of a one-sided curve, if you will. So if A is positive, then they're going to live above the x-axis, and if it's negative, it's going to be below the x-axis. The other thing that affects it is whether B is greater than 1, okay? Then from left to right, that's like having a positive slope almost, if you think of it that way. When B is greater than 1, then this is considered to be growing exponentially. And so from left to right, the same way we read all other things and all other graphs, it's going to be increasing very quickly. So if this is a greater than 1 value, you can think of that as kind of a positive slope. It means from left to right, our curve is getting very large. Whether it's getting very large in the positive direction or the negative direction depends on that A value. But nonetheless, it's moving away from 0, right? It's going either dipping down really into the really large negative numbers or into the really large positive numbers, okay? That's when the B is greater than 1. This is considered a growth, something that is getting larger, whether in the positive or negative direction, okay? If B is a decimal, remember, it can't be 1 and it can't be negative. So it's not going to be negative, but if it's between 0 and 1, so think decimal or fraction here. So that is between 0 and 1, fraction here, okay? Then it is decreasing, okay? From left to right, you could think of that almost like a negative slope when you're looking at this positive version, but it's getting closer and closer and closer, tinier and tinier and tinier, and getting smaller and closer to 0, okay? So you can see these guys just getting tiny and all the way closer to 0 as x gets larger in this direction. But that really brings up a super new and important concept. That's one of my favorite things to talk about, and that is the asymptote. So let's talk. This is probably the biggest thing today in our lesson, is this concept of an asymptote, okay? So before I talk about that, I want to tell you where this is coming from. So let's put that aside, okay? Let's just consider how this works. So exponential functions basically mean that instead of repetitively adding or subtracting like we do in linears, that constant rate of change where you're adding 5 every time or subtracting 7 every time, instead we are repetitively multiplying, because that's what exponentials do, right? They talk about repetitive multiplication. Okay, so if I'm repetitively multiplying by a number, then it's going to be exponential. Okay, now let's talk about that. Let's say that and sometimes you guys have seen an exercise that looks like this. You grab a sheet of paper. I don't know if you've ever played this game, but you grab a sheet of paper and you start to fold it in half, right? So I take whatever this original size was, okay, and I cut it in half or fold it in half. So now it's half the size. Okay, so there it is, choo-choo, right? And then I decide, I'm going to take half of that and I'm going to fold that in half. Okay, and now I've got this much, right? And then I'm like, I'm gonna fold that and take half of that. Okay, and you start to see what's happening here. This is exponential. I'm essentially cutting it in half or multiplying by 1/2. And then I could do it again. And I've heard, and I don't know if it's really true, that you can only do this 7 times on a sheet of paper. Yeah, you can't fold it further. And I already lost track of what I'm doing, of how many, but I've heard that you can only do this 7 times. So it'll be interesting and keep it folded, right? But you can see here, I'm like basically cutting it in half and repetitively dividing, which is the same thing as repetitively multiplying by 1/2. And then I multiply by half. This is definitely getting harder. Y'all get the idea here, okay? But I want y'all to think about this, okay? The question is, I could do this technically forever. Let's pretend that theoretically I could just keep going half and a half and a half. This would get infinitely smaller and smaller and smaller, okay? But would I ever not have paper left? That's the question, right? Would I ever end up at a place where it's like, there it is. I finally got to 0. I finally have no paper left. That actually wouldn't be true, would it? And we could think of that mathematically too. Like, let's say I start with a number like 8, and I start with 8. And let's say this, I'm going from 0 to 8 here, and then I take half of that, and that gives me 4. And then I take half of that, and that gives me 2. And then I take half of that, and that gives me 1. And then I can take half of that, and that gives me 0.5, right? And I could always cut the number in half, but here's the big idea. You can always take half of what you have and get a smaller number, get half of the original, but you would still always have something. You would never get to 0, right? You would basically get infinitely smaller. So think about that, right? And after 0.5, it would be 0.25, and then it would be 0.125, and then it would be 0.65, and you could just keep going, 0.065, and you could just cut it in half, and you can even, do this on the calculator if you got time. But you're going to notice that the number just keeps getting smaller and smaller and smaller. But because we're dividing, we always had a little bit left before, and we're taking half of that little bit, and we're going to have something smaller, but we're still going to have something. We're never going to get to 0, okay? And that is the big idea behind an asymptote. An asymptote is a line that represents a value that your function is going to infinitely approach, but never quite reach. So these guys, the way they're written right now, are going to get infinitely tinier and tinier and tinier. And so you think of this as like, here's my x-axis where y is equal to 0, and this curve is coming in, coming in, coming in, coming in. And the concept behind this is that it is literally getting infinitely closer to that axis, guys, but it's never ever going to quite reach it, because this is never going to be 0. Okay, it's never going to quite equal 0. It'll always just get infinitely closer. That's a pretty abstract but fascinating concept, and it is really at the heart of one of the big characteristics of exponential functions. Okay, they have asymptotes. Okay, and that asymptote is going to be a line that represents a specific value that our equation approaches, but will never actually be able to reach or be that number. Okay, and so that's and then we call that the asymptote. It's a kind of an imaginary line that your curve approaches infinitely, but never touches. Just gets infinitely closer to it. It's pretty mind-blowing. So in these particular problems, that is going to be 0, and we'll see why in just a bit, right? So it's kind of like the division problem, right? So whether we are, increasing and the asymptote happens when x decreases this way, or we're coming this way and it happens as x increases, for us, it's going to be at y equals 0, which happens to be the x-axis, but it's really because y is equal to 0. Because if I have a number, right, some non-zero number, and this is the big idea, if I have a number, starting number, and then I repetitively multiply by something, whether it's a fraction or a whole number, I'm never going to get to 0, ever. That's the big thing. So one of the big things I'll be looking for when y'all are actually working this out is that your curves approach but don't actually touch, or definitely not cross. Like that's definitely a deal breaker that says, oh, they did not understand this concept, or they weren't listening on the notes or whatever. But the big thing is this curve will never go across that x-axis. If it was living in that upper hemisphere above the x-axis here, then it's going to be there. Might infinitely get closer, but it'll never actually touch or go over it. At least not right now. Once we do transformations, it'll be different. But for now, it'll do that. So when you're graphing these yourself, it should look like this, where you can show that it's approaching it, but not actually reaching it or going across it. Okay. So I know I spent a little bit extra time on that, but that's this really real concept right there. Okay, so let's practice a few. We're going to determine if things are exponential from equations and from tables. So we'll talk about table patterns as well. So from a graph, we can already tell. This is what we'd be looking for as far as characteristics to decide if something is an exponential function. We'd be looking for that one-sided curve, whether it's going up or down, and increasing toward the right or to the left. But it would be a one-sided curve that approaches an asymptote. And then you would know, oh, yep, that's an exponential for sure. Okay, now let's talk about from an equation. So one of the major ways to tell is to make sure, first of all, that your x is your exponent, that the input x value or variable is the exponent of your function. Okay, so that's one of the first things we look for. Then we look to see that these other criteria are also met, that a is not 0, that b is not 1, and that b is positive. Okay, so let's try some of these. So if we check out number 1 here, let's kind of break this down, and that way we can make a sound decision, if you will. So the first thing I want to point out here is x in the exponent? So that's the question number 1, and the answer is yes. There it is. So x is in the exponent. Write that down. Remember, if I write it down, you write it down. Okay, so that's a big one. So then this is definitely a possibility. And then other things that I want to check for is, well, what is the a value? Well, the a value is the coefficient in front of the power. Okay, so in this case, a is what's in front of this 5 to the x, which is a -1. So in this case, a is a -1. My only requirement here is that a is not a 0, so this is still okay. All right, and then if I think about it, okay, well then what would be b? What would be b? b would be the base, right? So b is always the base of your exponential function. It cannot be a 1, and it has to be positive. So in this case, what is our b value? Our b value is 5. That is positive, and it is not a 1. So this meets all of the requirements. X is in the exponent, a is not 0, and b is a positive number other than 1. This is a yes, a definitive yes. Okay. Yes, this is an exponential. Okay. Let's try number 2. So is x in the exponent? Yep. What is the a value here? A is 1/2. That's okay as long as it's not 0. And then what is b? b is a -2. This is not allowed. Okay, we were told up here b has to be positive and not be a 1. So this is my deal breaker. And so this one is no, because b is negative. So no, because b is negative. Okay. Let's try this guy right here. First thing we want to check is x in the exponent? No, it is not, right? So because that's the case, the answer here is x is not in the exponent. So this is no. Okay, and that's a no. Let's try this last one. This one can be a little tricky. Okay, so if I have -2 to the x power, is x in our exponent? Yes, it is. Okay, so x is exponent. Okay, and then be really careful here, guys. If I think about what is the a value, so this does not have a parenthesis, so that negative is not part of the base. That means a is -1. Okay, and then b is just the 2. So you could think of this as essentially, if you have negative and then 2 to the x, that's the same thing as having like a -1 times 2 to the x. It was that whole dilemma of making sure or understanding the difference between having a parenthesis around the -2, like here. That's a deal breaker because you can't have a negative b, but this is not that situation. I don't have a grouping symbol. This negative is not part of the base. It's just a coefficient out in front. It's like having a -1 and then times 2 to the x. So that means here a is -1, b is 2. Everything here meets the criteria. So for this one, the answer is yes, this is exponential. Okay. All right, now let's talk about patterns in a table. So a while back when we were doing linears, we reviewed and we talked about how the pattern in a table for linears was a constant increase or decrease by the same quantity. So we would look for that common difference. If we were adding or subtracting the same amount every time, then we knew we were in good shape. Okay. These have a different pattern. We are looking here for repetitive multiplication. So we're going to look for a multiplication pattern. because that's what exponentials are all about. Repetitively multiplying by something instead. Okay, and so if we do that, sorry, my lighting's a little wonky. I'm not going to be really interested in whether this increases or decreases by the same amount. Instead, I'm interested in seeing what was the pattern from 8 to 4. Okay, well, from 8 to 4, it looks like they divided by 2, or you could think of that as multiplying by a half. Okay, from 4 to 2, that's also a division by 2, or in other words, multiplying by a half. From 2 to 1, that's dividing by 2, or you could think of it as multiplying by half. Okay, so if there's a constant repetitive pattern, and one way to do that is finding what we call the common ratio. So if you're not sure, you could just divide the new by previous. So 4 over 8, 4 over 8 is 1/2. 2 over 4, oh yeah, that's 1/2. 1 over 2, yep, that's 1/2. And so because I have that repetitive multiplicative pattern, this is definitely exponential. Okay, right there. On number 6, let's try it out. You could do the pattern, right? If I do 7 over 3, I just get 7 over 3. Let's just leave it like that. Who knows? Yeah, that's what, well, I guess if we, that'd be 2 and 1/3. That would be multiplying by there. And then we do 11 over 7. That's not equivalent to that. Okay, that'd be multiplying by 1 and, what is that, 4/7. That's not the same common factor, okay, multiplier. This one would be 15 over 11, which would be 1 and 4/11. So this is not multiplying by the same number every time. I can't multiply 3 times a number to get 7 and then do the same one to get 11 and so forth. This is not exponential. We could test for linear. We could see, is it increasing by the same? Oh yes, it is, right? So if we look at the pattern here, oh, this was +4, this was +4, and when this was +4. No wonder it didn't work, because it's not exponential. This guy is linear. Okay, so it has a linear pattern. They're adding 4 every time. The multiplication wouldn't work here. It was not a multiplicative pattern, right? Let's try this guy right here. If we look at this example, let's see, I could think about what, 0.125 times what gives me 1/2. 1/2 times what gives me 2. And what 2 times what gives me 8. So looking at that multiplicative pattern, you might find, oh yeah, it's times 4. 0.125 times 4 is 1/2. 1/2 times 4 is 2. 2 times 4 is 8. Or you could have grabbed your calculator and done 0.5 divided by this, and you'll get 4. 2 divided by 1/2 is going to be 4. 8 divided by 2 is going to be 4. And so because you have that multiplicative pattern, this one is definitely exponential. Okay, and then here, let's take a look. Do we see a pattern in the problem? We've got 12, 9, 6, 3. This looks to just be decreasing by 3 every time. So 12 minus 3 is 9, minus 3 is 6, 6 minus 3 is 3. This is a linear again. If I try doing the ratio test that we just came up with, it wouldn't work, because 3 over 6 is 1/2. 6 over 9 is 2/3. Those don't match, right? And then 9 over 12 would be 3/4. That would also not match. So it would always have to be the same number. So that's having a constant ratio instead of constant change. Okay, so that's what we're looking for. We're basically looking for a multiplicative pattern. And if so, then you have an exponential function. So these back ones, guys, are going to be practice, and we're actually going to practice these in class tomorrow. So I would love for y'all to try a couple of these. In fact, the ones that I'd like for y'all to try, but you're going to bring them down in class. You're going to try number 9. You're going to try number 10. And I'm thinking we're going to go for number 13. And then I want y'all to try setting up a table. But we're going to discuss these together. The main thing was just introducing the concept of an exponential function, and what does that look like as a graph, what does it look like as equations, and what does that look like in table form. And those are the characteristics for exponential functions. One-sided curve that approaches an asymptote, equations that have x in the power and meet these criteria for a and b, and a table that has a multiplicative pattern generating our values. Those are the characteristics for exponential functions.